So let's go back to our usual roadmap. So today we are going to still focus on closed loop methods for optimal control, particularly through the lens of dynamic programming in a discrete time formulation. But we're going to extend the formulation to the setting whereby we have uncertainty in our system. Particularly, we're going to reason about disturbances that might affect the forward propagation of the dynamics for the state. The setting that we're going to discuss is a very famous one and is referred to as the Markov decision processes setting. So specifically, remember the problem formulation we've been discussing for the past 2-3 lectures. So now we are in discrete time. So the update equations for the state are written as sk plus 1 equal f of k sk uk. So this would have been the setting until the previous lecture. But now we are adding an additional element, wk. So wk is referred to as a disturbance. It is something that affects the forward propagation of our dynamics, and depending on the specific application, might have different meanings. For example, if you want to control an aircraft, wk could be environmental uncertainty, for example, wind gusts. If we are trying to control the financial market, like basically we want to decide how to buy and sell stocks, wk might represent the underlying uncertainty within the market, and so on and so forth. So the idea is that you observe the state x of k, you take a control uk, and then nature is going to pinpoint a value of wk. This order is somewhat arbitrary, but you have to fix an order in order to make this model actionable. Now, as it was the case of the deterministic setting, we are still assuming that the controls need to belong to some set capital U. That is, our set of controls is in general constrained within some set capital U. Now, the disturbance W are quantities that are computed by nature in a way. And so they're modeled as random variables. And we do place a key assumption on the distribution of such random variables W. Specifically, we assume that the random variables wk are distributed according to some general probability distribution. It could be Gaussian, it could be anything. That can be conditional on the current value of the state and the current selection of the control. So you are in a state, x of k, you get to see that state. You pick a control u. Based on that, there is some realization of the disturbance value. Of course, in some setting, actually this probability distribution does not need to depend on x and u. That's perfectly valid. What is important, though, is that this probability distribution is not allowed to depend on previous values of the states. So it's not allowed to depend on sk minus 1, sk minus 2, and so on. So it's not allowed to depend on the history of the process. That's a fundamental assumption we are making in our model. It's typically a good assumption, meaning that the realization of your disturbances and essentially uncertainty in your environment only depends on the current state and current selection of the control. But for example, if you're driving, what the other pedestrian might do next could be modeled as a disturbance. And of course, what the pedestrian is going to do next depends on where we are with our car and what we plan to do, turning right or left. So, sort of makes sense. But there are cases where actually you would like to model the dependency on the previous values of the states. Well, that's not allowed in this problem setting. So it's a restriction, but it's a mild restriction. Again, why do we place these restrictions in our settings? Is to find a good compromise between generality of our problem formulation and the problem formulation that allow us to do some computation. Basically, derive some recipes to compute our control policies in an actionable way. I'll come back to this assumption later. As it was the case of the deterministic setting, we are interested in closed-loop control. So we are interested in finding controls that are expressed as a closed-loop policy. So a function pi that maps any state in the world into an optimal control action. And finally, the last ingredient in our problem formulation is the cost. So the cost is going to be expressed as the summation of a terminal cost, as usual, plus stage-wise cost, as usual. Now, the stage-wise cost could actually depend on the disturbance. We'll see some examples later. And importantly, since you have a dependency of the cost on the disturbance, that cost itself is a random variable. So you want to translate that random variable in something deterministic that you can minimize or maximize depending on your setting in order to define a notion of optimality for your policy. To do that, there are different ways to do it. We, in this problem formulation, select to compute an expectation over the cost. The expectation is with respect to the realization of all the disturbance variables. Make sense? So main differences here are that the state transition function depends on a disturbance W. W is a random quantity with an arbitrary probability distribution that is constrained, though, of being only conditional on the current value of the state of control. It cannot depend on previous values of the state. And the cost is allowed to depend on the disturbance, but since we have such a dependency, all this term is now a stochastic quantity. So to reduce it to a deterministic quantity we can optimize over, we take an expectation of it. And then the problem is to find a policy pi that optimizes such a cost. So any questions here? So this is important we are all on the same page, otherwise everything I'm going to discuss next is not going to make much sense. Yeah?
Just to clarify, you said that at each stage the disturbance value could be dependent on the disturbance in the prior stage?
Unless only indirectly through the state. So the state mediates your dependency on the history. Of course, the evolution of the state depends on the disturbance. But everything that is related to the history of the process, so previous states, previous controls, previous disturbances, all of that knowledge is mediated through the realization of the current state. Yeah?
Does the cost change depending on when you sample WK?
Yeah, absolutely. Like, for example, you are trying to control an aircraft. Depending on what the actual realization of your wind profile is, the cost of the trajectory is going to change.
Right, you only factor like once, I guess, during your iterations.
No, the problem is that you want to find a policy that is optimal with respect to all possible realization of those uncertainties. And one way to collapse all those realization of those uncertainties in the number you can optimize over is to take the expectation of your cost with respect to all possible realizations. So maybe sometimes you are unlucky, sometimes you are lucky, so you want to compute the policy that, on average, is going to do good enough.
I didn't realize that was like the function.
Yeah, so it's the expectation over all realizations of the disturbances at time 0, 1, 2, all the way to n-1. Other questions here? So this is the setting of Markov decision processes. Now, there are variations, right? So as we will discuss later, maybe you're not just interested in the expected value of your cost. Maybe you're also interested in expectation plus some notion of variability. So you want to make sure that on average you do good enough, and there are no cases whereby you could do terribly poorly. Or another setting that we're not going to cover in this class is rather than modeling the disturbance as a stochastic quantity, to model it in an adversarial fashion. So assuming that at every point in time, the disturbance that is realized is the worst possible. That leads to minimax problems. There is no stochasticity. Basically now becomes a game against nature with some sort of game theoretical interpretation whereby you try to compute an action and nature tries to compute the other action that is maximally damaging. Anyway, we're not going to see those settings. Markov. So Markov me. Markov is I did not come up with this formulation, unfortunately. Otherwise, I would receive a couple Nobel Prizes.
I know it's relying on like one-time stuff. Oh, like I guess it's relying on it.
Yeah.
I'm just curious why they don't expect you to post some sort of presentation of like
So, because remember that when we compute the cost is additive. It takes into account the cost of the full state trajectory. But the cost of the full state trajectory depends on the realization of all the disturbances. That said, the state evolution is only affected by the current realization of the state. And as we will see, dynamic programming will try to break down this complex cost that depends on all these nested realization of the disturbance into expectation with respect to each one disturbance at a time. Does this address your question? Somewhat. Yeah.
Does it rely on does the state rely on the previous types of only?
Well, as I was telling your colleague, keep in mind that once you move into the new state, sk plus 1, sk plus 2 is only going to be affected directly by wk plus 1. But sk plus 1 came from here, and xk plus 1 was affected by wk. So you can see how sk plus 2 has a direct dependency on wk plus 1 and indirect dependency on wk. So actually each state does indeed depend on all previous disturbance realizations, but directly only on the most current one. At least in this formulation. That's how we set out the problem. Does it make sense? So sk plus 1, 2 does indeed depend on wk, absolutely. But that dependency, as I was telling to your colleague before, is mediated through the realization of the state sk plus 1. All right, so a few key points. So this is discrete time model, obvious. Is a Markovian model. Markovian model means that we do not have an explicit dependency on the history of the process. Everything is mediated through the current value of the state. Practically, what that means is that the probability distribution for the stochastic disturbance can only depend on sk and uk. Cannot depend, for example, on sk minus 1. The objective is to find a closed loop policy. In a stochastic setting, this is even more important since stochasticity is bringing us left and right. So you really want to have a policy that maps wherever you are in the state space into a control, to optimal control action. The cost is additive. That's usual. That's same as in the deterministic setting. And we use a risk-neutral formulation. What does that mean? That in order to compute the cost, here we take an expectation. We do not model additional considerations, such as, as I was saying before, variability with respect to the average. In some settings, for example, even as a human, when you try to optimize your life, you try to optimize for your average income if you met a bet, but also you try to protect yourself from the worst case or from excessive variability. So this formulation is not doing that. It's only modeling what is going to happen on average. There are more sophisticated formulations referred to as risk sensitive when you add additional terms, such as, for example, a variance term and so on. The problem with those formulations is that they make computation much more complicated. In their most, naive, in the most naive approaches, standard dynamic programming equations no longer hold. The principal optimality no longer holds. So you need to do, additional analysis in order to come up with practical algorithms. Actually, this is a topic I've done quite a bit of research in the past. Anyways, for this class, we're only going to focus on a risk-neutral formulation. The reason why the expectation is nice is intuitively the expectation is itself a linear function. So it allows you to chop the problem in multiple stages to be very practical. But we'll see that in a second. Now, as I've also mentioned some time ago, different communities use different notations. So UK is a typical notation in controls. Computer science typically use the notation AK. A stands for action. XK is the typical notation for the state in control. Computer science typically uses S of K. The probability, so the transition equations are typically written according to a transition function that says what the value of the next state is depending on SK and AK. So this is analogous to what we brought here. And there are additional terminologies from other communities, like for example, from operations research and so on and so forth. Fortunately, there is a paper which is called OR stands for Operational Research and Control Theory, a Rosetta Stone for stochastic optimization. So if you get tripped by the notation among different communities, this is a good paper. Our only job is to say, that's a symbol we use in control. That seems crazy, right? But I mean, these days probably you just go on ChatGPT. When I first had this reference was a few years ago, ChatGPT was not there. But anyway, the point is, different communities use different terminologies, don't get tripped. Now, the good news is that because of the way we formulated the problem, specifically, we use the expected value operator to map the random cost into a deterministic quantity we can optimize over. And critically, we make the Markovian assumption. Intuitively, these two assumptions allow us to chop the problem into pieces. Chopping means the principal optimality. Specifically, and the intuition is the same, we're not going to derive it, but the proof is not too complicated. Assume that you have an optimal control policy pi star. That means that we have an optimal policy at time 0, pi star 0, 1, optimal policy at time 1, pi star 1, optimal policy at time n minus 1, pi star n minus 1. So an optimal policy is indeed the sequence of n policies, each one mapping the current state into the current optimal control. Consider the tail subproblem. We are at some state, S of k, and we only care about what happens after time k. Then the truncated policy is, we start at time I. K is still the random subscript. We start at time I with the state x of I, and we look at the tail problems from time I all the way to capital N. Then the tail policy, so the sequence of policies from time I to time n minus 1 is optimal for the tail problem. Intuition the same as in the deterministic setting. The proof a little bit more involved. If you're interested in the proof, a good reference is represented by the work of Dimitri Bertsikas. Basically, his optimal control books. They're also referenced in the syllabus. He provided proof, nothing particularly insightful, so we're going to skip it. But of course, as any result, it has to be proven. Any questions here? So per se, the principal optimality is not so useful. It's something interesting to know, but it doesn't really land to an actionable algorithm. My point here is to show that, to highlight, this problem has a specific structure that allows us to get to an actionable algorithm, which is really dynamic programming, but extended to the stochastic setting. And as we will see in a second, the dynamic programming algorithm in a stochastic setting has exactly the same form of dynamic programming in a deterministic setting. So we start from the end, and then we start solving the problem going backward one stage at a time. Easy thing to do is just to show how the algorithm works. We start from the last stage, capital N, and we set the terminal cost, Jn x of n, as the terminal cost in our cost formulation. And then we go one step backward recursively, where at each time stage k, for a given state s of k, we try to find the optimal control uk that optimally trades off the current cost and the future cost to go. So same as a deterministic setting with the two differences. The transition function now depends on wk. Well, that's obvious. That's how we set up the problem. Remember that this is sk plus 1. jk plus 1, sk plus 1 is the cost of the optimal problem, the tail problem, that starts at time k plus 1 at state sk plus 1. And then the key difference with respect to deterministic setting is that this quantity is stochastic. The current cost in general depends on wk. And the cost to go, it's also stochastic because the transition to the next state is stochastic. But, so we have to take an expectation with respect to wk. But importantly, in this computation, we only take an expectation with wk as opposed to the full sequence of disturbances from time 0 to time n minus 1. So it's a dramatic simplification. So you carry out this computation for every stage k and every state s of k. And once you are done going backward all the way to time 0, j star x0, so the optimal cost of the problem you're interested in, starting from state x0, is equal to the end solution of this recursion. And the optimal policy is constructing by setting pi star s of k as the minimizer of the Bellman recursion. So same as the deterministic setting, only difference is that now you have to deal with the disturbances.
Previously, when we made the assumption that the distribution of the disturbance does not depend on the first factor, it's the purpose of that to ensure that the optimality principle.
That's right. Correct. So in a stochastic setting, in order to keep the structure, you still need that additive structure on the cost, but then you also need the Markovian assumption on the distribution of the disturbances. That allows you to derive dynamic programming equations to solve the problem. And for the proof of it, I referred you to the books of Dmitry Bersikas, who is a celebrated professor at MIT. Actually, I was his course assistant when he was teaching dynamic programming at MIT. Any questions? Let's do an example, just to fix ideas about what's happening here. So let's consider the following problem. So this is the inventory control problem. So you have a warehouse, and you are storing some stock. You're purchasing some new stock and anticipating future demand. And of course, once demand for that stock is realized, then you ship it. So we now model the problem as follows. So we let SK, that's our state, be the stock available. For example, number of refrigerators, if our warehouse is storing refrigerators. Inventory UK is the number of additional items that we get, anticipating future demand. And WK is the demand that gets realized at time K. The state at time K plus 1, so the number of units of stock that are available at the next stage, is given by how much stock I have right now, plus the stock that we purchase, and we assume that once we purchase it, it gets immediately delivered, minus the demand. So if we start with 2, we purchase 1, we go to 3, Then we have a demand of 2, so we ship 2 stocks out. I'm left with 1 at the next stage. If the demand is larger than the stocks that I do have, then the number of stock at the next time stage is equal to 0. And the demand that is unfulfilled, it's unfulfilled. So that's why the transition dynamics have the maximum between 0 and SK plus UK minus WK. Now our warehouse is very small, and so the maximum amount of stock we can keep in our warehouse is equal to 2, which means that SK plus UK is less than or equal to 2. Of course, this is a toy problem. The reason why I'm making this assumption is since I'm going to do the dynamic programming recapture by hand, and I have to do it for each possible value of the state, I don't want to do it for 25 different values of the state. I artificially somewhat decrease the state space. Now, what about the disturbance? We need to specify a probabilistic model for the disturbance to have a complete problem formulation. So in this setting, I'm assuming that the demand, which is our disturbance or our stochastic element in the formulation, does not depend on the control nor state. So it's a simple setting. Specifically, we assume that at time k, we have a 10% probability that we have no demand, 70% probability that we have demand for 1 unit, and 20% probability that we have demand for 2 units. Of course, the probability distribution has to be normalized, so the probabilities has to sum to 1. And finally, we have to set up the cost. So the cost is defined as 0. So we assume, first of all, that we are going to optimize operations over an horizon of 3 steps into the future. And we assume that the terminal cost is equal to 0. So no matter how much stock I'm left with at the final time, I don't care. I just dispose of it at no cost. So the terminal cost is 0. And then the stage-wise cost is as follows. Is UK, so we assume that we spend $1 to buy 1 unit of stock, plus a quadratic term. So this quadratic term has the following interpretation. If after I purchase UK units of stock, and then the demand WK gets realized, if this quantity is positive, meaning that I have a positive amount of stock that I have to keep until the next stage, that's an undesirable situation because, of course, storing stock is expensive. And I penalize that with the square of that value. So that's the interpretation if this quantity is positive. If this quantity is negative, means that the demand is larger than the amount of stock that I have available. I still penalize this quantity with a square because, of course, not fulfilling demand is also an undesirable situation. I, for example, damage the trust of my customers. Of course, this is somewhat arbitrary, and in general, how you set up the cost is arbitrary. You just try to inject some notion of how happy you are with respect to different conditions. Notice how all of this depends on the realization of different disturbances at time 0, 1, and 2. So I transform all of this into deterministic quantity by taking expectation over W0, W1, and W2. So now the problem is you are an operator for this warehouse. What is your optimal policy? So for all possible realization of the state, say that at time 2, it just so happened that x2 is equal 1. What is the optimal thing that you should be doing? You buy 1, you buy 0, what do you do? Yeah. It depends on the current amount. So basically how much stock you have run on your stock. So if at time 1, you have 1 unit of stock, what do? Do you purchase 1 additional unit of stock, or you do not? But keep in mind the sequence of events, how we have specified it. So you get to observe the state, so you know that time 1 you have x1 unit of stock, but you don't know your demand yet at time 1. Then you have to select how much stock you want to purchase, and then the demands get realized.
So in this case, I don't think you would buy the stock because if you
expect it to be a demand of 1. You just keep it 1.
Well, why you say that you expect a demand of 1? You expect a demand of 1 with 70%. But it's also possible that you get 0 with 10%. And it's also possible that you get 2 with 20%. So it's not so clear cut. So what you know is not what the exact realization of disturbance is probabilistically what the realization of the disturbances might be. So that's a knowledge you can leverage. I mean, which is natural, right? So when you invest in stocks, you don't know exactly what the return on your Tesla stock is going to be. So it says beginning of the day, you don't know what the return of the value of your Tesla stock is going to be at 12 p.m. I try to anticipate that. So you have some probabilistic model. Based on that, you want to optimize operations. Yeah.
What do we pose? So you said the constraints translates to not wanting 2 units, more than 2 units in the factory.
Yeah.
But why does this translate on a constraint on the action as well?
So, well, here, basically, I'm modeling that at the maximum, you can have 2 units of stock. So your warehouse has some physical limit. It can't have more than n units. So how much you store in the warehouse is how much you have right now, plus how much you purchase and gets delivered immediately. So that's the meaning of this constraint. But there is also pedagogical meaning about why you use this constraint. So this is a setting whereby UK, your control, is constrained by a function of the state. So this is a case whereby the explicit dependency of the set capital U on SK arises.
No, what was it clear to me is that isn't your stock XK plus UK minus WK or only XK?
Well, the reason is that, so this is your warehouse. And you have this amount of stock. And you have only this space here. Then you purchase with U this space here. And then the demand is realized afterwards. So it's not like immediately realized. So basically, there is a moment in time where you can't really fit more stuff in there. Yeah. So think about W as something that happens after a non-infinitesimal amount of time after you purchase your stock. Again, some of these assumptions can be changed, right? Here, I want to give you like a realistic example, but also something that is manageable to, and also highlight some of the features of the problem formulation. So the question is, how do you solve this problem? So the way you solve it is by being disciplined and running a dynamic programming recursion. So specifically, you set the terminal cost J3x3 as G3x3. And for this problem formulation, we said that this terminal cost is equal to 0. This is by how we define the problem. So, and then you start going one step backward in time. So now we have J2x2 is equal to the minimum over U2 has to be greater than 0 and has to be less than or equal to x2 minus 2. So it's the control constraint that we're discussing. Expectation over W2 of G of x2 U2 W2 plus G3 x3. Okay. Now, from the recursion, we know that this is equal to 0. So we write down this explicitly. What we get is J2x2 equal minimum of U2 between 0. I cannot buy negative amount of stocks. and x2 minus 2 because of the capacity constraints in our warehouse, expectation with respect to W2 of, now I'm going to write down the stage-wise cost explicitly. So this is going to be equal to, it's going to be equal to U2, right? Plus x2 plus U2 minus W2 squared. There is no cost to go because I already set that the cost to go to G3 is equal to 0 because of the previous recursion. Well, I use the boundary condition. Any questions here? Yeah. 2 minus x2. Yeah, 100%. Sorry about that. That's absolutely correct because the constraint is U2 plus x2 less than equal to. Yep, thank you for noticing that. All right, so now that you have written down the Bellman equation for state x of 2 at stage 2, now you have to solve it for all possible values of the states. What are the possible values of the states? 0, 1, and 2, because you can't have more than 2 stars. So which one? Okay, so let's do it for J20. So of course, in general, a computer would do it. But it's useful for you to carry out some of these Bellman recursions by hand. It's a bit annoying. There is no cleverness or smartness, nothing. But it's helpful in order to better appreciate what's happening here. Practically, in your final exam, I would ask you to carry out a Bellman equation by hand. So I like to say it's like a vaccine. It's a bit annoying, but you do it once, and then you are fine for life. So do it. Anyway, so let's do it for 1, then maybe you can do it for J21 or J22 by yourself. So for J20, so now we have minimum over U2 greater than or equal to 0. Now we are solving the tail problem where x2 is equal to 0, which means that the constraint is now U2 less than or equal to 2, because we are plugging 0 into x2. So U2 between 0 and 2 of expectations with respect to W2 of this quantity here. So what's the expectation of this quantity? Well, with a 10% probability, W2 is equal to 0. So with 10% probability, so this is a random variable. Its realization is, for a given selection of U2, is U2 plus x2 is 0 plus U2 minus 0 squared. I mean, I'm a bit pedantic here, but. So that's the case where W2 is equal to 0. Plus, then I had the case where W2 is equal to 1, which is 70%. So plus 0.7. I mean, as an aside, the expectation of a random variable x is equal to the summation of, for I equal 1 to n, of what? So if you have random variables, I can take n values xi's, each one with probability pi's. Yeah. So that's what I'm doing here. So it's 0.7 of U2 plus the state is still 0 plus U2 minus 1 squared. And then I have a plus should be 20%. So 0 plus 0.2 of U2 plus 0 plus U2 minus 2 squared. And now I have to find the U2 that minimizes this expression. So does this make sense? Essentially, I have unrolled the expectations with respect to the three possible realizations of the disturbance W2, each one weighted with its respective likelihood of happening. Yeah?
And if we started with an initial stock value of 1, then all of the first terms in those parentheses should go 1, right?
1, 1, 1. Yes. And here you should also change the constraint set, because now U2 can only be between 0 and 1. You get 2 minus 1. So you have a change here too. The probability distribution wouldn't change because we're assuming that the probability distribution is not conditional on the exact value of the state. So these numbers will be the same. Okay, so this becomes J20 minimum over U2 between the 2 and 0 of 0.1 U2, 0.7 U2, 0.2 U2. Of course, probability sum to 1, so this is equal to U2 plus U2 squared times 0.1 plus 0.7 U2 minus 1 square plus 0.2 U2 minus 2 square, which is exactly what you have here. So you plug U2 equals 0, you get a value. You plug U2 equals 1, you get a value. You plug U2 equals 2, you get a value. You pick the U2 that gives you the lowest value. It just so happens that the optimal choice is 1. So that means that if you happen at stage number 2 to be in state x2 equals 0, then the optimal thing to do for you is to purchase 1. And kind of makes sense. That's also what your colleague was hinting at. That since we have such a high probability that we have a demand of 1, you want to buy an additional stock so that you can fulfill it. So it's not too surprising. Anyway, so it turns out that if you do this computation now for the state equal to 1, the state equal to 2, and then you go back to J1 and J0, the optimal value for each possible initial condition is as follows. So I would encourage you to do some of this computation, maybe not all, but at least some of them. The result for each recursion, for each possible state, stage is in the spreadsheet that I've linked here. So just click on the link and you get a spreadsheet with all the values so that you can cross-check that what you're doing is correct. Yeah, keep in mind this is a cost. So in general, the lower the better. So yes, state 1 will be the best to start with. Which again, kind of makes sense. It's in between, so you're not at risk of a missing demand, but at the same time, you don't have to buy a lot of new stock. So roughly speaking, it's not too surprising. It's something in the middle. For this specific problem is a good place to be. So short answer is yes.
So does this give us like the optimal policy to take from any state that we're in? If we move into like perhaps 1 to 2, and then just like we have something from like W, we ignore demand. What we have to reevaluate?
No.
It is going to be
optimal policy because of the visual optimizing. So as you go back, all the data star problems have been self-optimized. So no, the sequence of policy by 0, by 1, by 2 are always going to give you the best optimal thing to do at all stages, all states. You don't have to re-optimize anything. So that's pretty powerful. Yeah. So that's a little bit of a problem with dynamic programming. As you'll see in the homework, it does provide significant computational savings with respect to brute force optimization, but still, is pretty time consuming, particularly because you have a dependency on the number of states. So in this case, the state is one dimensional. X can only, it's just one number. But if now X is a pair, then you have to, your scaling goes quadratically and cubically and basically exponentially with the number of dimensions in terms of how many computations you have to carry out. In this case specifically, it's 9. It's basically 3 for the states, and then you have to go, you have 3 stages. So 3 by 3, yeah. 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 So if you have a continuous state space, you cannot run this algorithm because you cannot enumerate all possible states. So you can do a few things. So one could be discretizing your states, of course, or map your state representation something lower dimensional and then discretize it there. But yeah, at some point you have to get to something you can do numerical optimization of. Let's look at another example. So our preferred problem, which is LQR. So we're going to look at LQR with yet another twist. So same setting as before, we have a quadratic cost. Only difference is that now our dynamics are affected by a disturbance W, which is a stochastic quantity that is distributed as a Gaussian variable with a 0 mean and a covariance matrix sigma. So LQR problem as before, only difference is that the dynamics are now stochastic. So the question is, can we use dynamic programming to solve this problem? The answer is yes, in a way that is extremely similar to what we did a couple of lectures ago. Specifically, the way it works is that, inspired by what we know from the solution to LQR in a deterministic setting, let's assume that the cost jx, jk, xk is equal to some quadratic, plus possibly some constant, let's call it ck. Remember that for LQR, there is a typo here. This should be pk plus 1. I'll fix that. So remember that in a standard LQR, the cost to go is quadratic. It's a quadratic form on the state. Okay. So, oh, come on, another typo here. So this should be sk. I don't know what I was thinking. So this should be jk or sk, and this should be xk plus 1, pk plus 1, sk plus 1. So I'll fix these two typos. So how do we solve this problem? We write down the Bellman equation. So jk xk, again, k plus 1 is a typo here, is equal to mu of uk, expectation of wk, stage-wise cost plus cost to go. So assuming that cost to go is a quadratic, so is sk plus 1, pk plus 1, sk plus 1, plus a constant, I'm ignoring it here. Now let's unroll this multiplication. Here I'm quite fast because this is essentially something we already covered. So we have a x bu pk ax plus bu. So that's exactly the quadratic term we had in standard LQR. Plus I have the quadratic term in wk, which is here. Plus I have the cross terms between ax bu and w, which is here. And I have two of them. So this is just by unrolling this multiplication. So now I'm taking the expectation of this quantity. So this is a constant. So its expectation is exactly xqx. This is a constant, so the expectation is the same quantity. This is also constant, does not depend on wk. The only two things that depend on wk is this term and this term. This term is linear in wk. And we're assuming that wk is 0 mean. So the expectation of all of this stuff is 0 because the expectation of w is 0. So if you have a random variable, say that you have a times x, you know that the expectation of x is equal to 0. What is the expectation of ax for a being a real number? 0. A times expectation of x. Expectation of x is 0, so this is equal to 0. So that's exactly what's happening here. Oop. What is it? Here. Okay. The term that is not obvious is what is the expectation of w pk plus 1 w. So it turns out, we're not going to prove it, basically relies on some basic facts related to linear algebra, is that the expectation of w pk w, where w is a Gaussian variable with covariance sigma, is equal to the trace of pk plus 1 times the covariance of w. Remember that the trace is equal to the sum of the elements of the diagonal of the matrix. This is not obvious. I'm just giving this to you as a fact. So basically, I'm telling you that the expectation of W transpose pk plus 1 wk is equal to the trace, which is the sum of the elements of the diagonal of a matrix, of pk plus 1 times the covariance sigma of the variables wk. That we assume we know, because we assume that we know that this disturbance is at 0 mean and with a given covariance sigma. The proof requires 2-3 steps, not particularly insightful, so we're skipping it here. The point I want to make here is that look at what we found, that the right-hand side of the Bellman equation is exactly the one that we had in LQR plus a constant term. So these are quantities that we already know. pk plus 1 from the computation that we already carried out at time k plus 1. And sigma is part of our modeling knowledge. Which means that when we try to find the optimal control U, what would be the solution? Is exactly equal to deterministic LQR plus a constant. So when I try to find the optimal control, I take the derivative with respect to U. The constant goes away because it doesn't depend on U. So the solution that I will find is exactly the solution that we found for LQR, linear feedback on the state. I plug that back into the cost. I get a quadratic with respect to the state plus a constant. So we started from a cost to go time k plus 1. It was a quadratic plus a constant. I get again a quadratic plus a constant. So all of this to say, without spending too much time here, is that for stochastic LQR, the control policy is the same. The cost is almost the same. The only difference is that the cost is increased by some constant related to the magnitude of the noise, which kind of makes sense. We have to pay something because now we are operating in an uncertain setting. Anyway, this was just one other example to showcase the use of stochastic dynamic programming for the LQR problem. Yeah?
This is a deterministic case if the covariance was dependent on the control.
Yeah.
Like the probability is like a function.
Yeah, of course. Because now, once you start taking the derivative with respect to U, this term wouldn't go to 0 anymore. So actually the formulation, yeah, absolutely. What we exploit here is that sigma is just a given quantity that does not depend neither on state nor control. Cool. All right. So one additional item, maybe we're going to conclude this item on Wednesday. This will become important when we move into the second part of this class, namely reinforcement learning and imitation learning. So far we have introduced stochastic optimal control problems or optimal control problems in a finite horizon setting. So basically we assume that we are optimizing operations over 15 steps, 20 steps, 35 steps. But as we will see, for a number of reasons, the RL problem, or the indication learning problem, particularly the RL problem and person learning problem, is formulated within an infinite horizon setting. So we assume that now we're trying to optimize operations over an infinite number of stages. So the number of stages is infinite. Now, of course, the assumption of an infinite number of stages is never fulfilled in practice. Of course, our lifetime is limited. The lifetime of the universe is arguably limited, but is a good approximation for those problems involving a finite but a very large number of stages. And as we will see, it simplifies the problem considerably. So it's again a sort of a compromise between being something that is quite reasonable in many settings and also simplifying the problem even further. Specifically, an infinite horizon market decision process is a problem whereby, as usual, we have a state X, or in a computer science notation S. We have an action U, and we have a transition function that tells us what the next state xt will be, given the current value of the state xt minus 1 and current value of the control ut minus 1. Now, since we're getting closer to the RL formulation, typically in reinforcement learning, people don't talk about cost, they talk about rewards. So instead of minimizing a cost, we maximize a reward. That is just a minor modification. Each problem can be mapped in the other one by just swapping minimization with maximization and adding a sign minus in front of the quantity you're interested in. We introduced the notion of discount factor gamma. I will talk about it shortly. And so an infinite horizon problem is defined by these 5 quantities here. We knew 4 of them. There is a 5th one I'm introducing gamma. I'm going to explain it in a second. The point I want to make here is that now everything in this formulation is stationary. What that means is that the transition probability from the state at time t-1, a control at time t-1, into the state at time t does not depend on the specific stage t-1. Remember that before, the transition model was allowed to depend explicitly on time. So even if you have the same state, same control, and you have the same relation to disturbance today and tomorrow, in general, the transition to the next state might be different. In infinite horizon MBTP, we're making an assumption that the problem formulation is stationary. Why do we make a stationary assumption? One, again, because oftentimes it's a decent one for processes whose dynamics don't change dramatically from stage to stage. But 2, in infinite horizon MDP, as you can imagine, we are trying to use some limit concept. And so doing limits when the underlying problem formulation changes, it will be very, very hard. So, again, compromise between being reasonable and making computation feasible. Now, our goal is to find a policy that optimizes the expected cost to go. But now we are, reward to go. So now we're talking about rewards and non-costs. And now we have this additional term gamma that multiplies the reward, gamma to the power of t. So gamma is a number between 0 and 1, as referred to as a discount factor. So why do we multiply our reward by this constant to the power of t? We didn't have that in the finite horizon formulation. Any hypotheses about why people do that? Exactly. So that's the intellectual explanation that in general, when you try to optimize operations, you, of course, place a lot of emphasis on the consequences of your decisions in the next few time steps. You don't care too much about what the consequences might be 1 month from now or 1 year from now, which kind of makes sense. But as usual, there is also the pragmatic explanation. What is the pragmatic explanation? Exactly. So since now we are in an infinite horizon setting, So this is a sum from 0 to plus infinity. And so in general, for any reasonable reward, this will be equal to plus infinity. So if all policies have a cost equal to plus infinity, which one is optimal? They're all plus infinity. They're all phenomenal, right? So that's why and you put like an exponential weighting, because typically exponentials kill a lot of functions. It's a recurring theme where people pre-append the quantities of an exponential to ensure convergence. Anyway, just wanted to highlight why people use a discounting factor. Again, it makes sense, but also practically. There is a question? Do you have a question?
Oh, no, I think we're good.
Okay, great. So, infinite horizon MDP, problem is stationary. We're now focusing on rewards. We have this addition of a discount factor in our modeling. Now, since the problem is stationary and we are on an infinite horizon, the policies, the optimal policy, doesn't depend anymore on the stage you are at. So you don't have a P0, P1, P2 anymore. You just have pi. So we're just optimizing over pi. A mapping between state at any stage in time into a control action. Remember that before we were optimizing over pi0, pi1, pi2. Here we just optimize over a single pi. Because a stationary policy, that is a policy that does not depend explicitly on time, is indeed optimal. Yeah.
Are you saying that the optimal policy has to be stationary? In this,
We focus only on stationary policies? Yes, that's what we're saying here. Correct. Okay, so then the question is, how do we solve such problems? Guesses? Well, we try to reuse whatever we learned from a finite horizon optimal control, which is the notion of a Bellman equation. So, trying to exploit that intuition, remember that when we were in the finite horizon setting, we said that the optimal costs or optimal rewards satisfy a recursive equation. So it's natural to wonder if an infinite horizon setting, if you let the number of stages to go to infinity, basically you take a limit on both sides, that stuff will converge to something. So basically remember that you have JOK xk is equal to maximum over UK of expectation over WK of, actually let me do it with the cost, since we were talking about cost with the J formulation. Oop, there is a GK xk UK WK plus JK plus 1, SK plus 1. So, assuming our problem is stationary, does this stuff converge to something? And if this stuff converges to something, and I take the limit here and here, do I get a sort of a stationary Bellman equation? The answer is yes. So actually, the cost function in the limit that the horizons go to infinity does converge to a steady state quantity. And that steady state quantity satisfies not a recursive equation such as there, but a fixed point equation, which is represented here. So this is the extension of the Bellman equation to an infinite horizon setting, whereby V, which is the same as J, but when people talk about rewards, they like to refer to it as V. V stands for value. So reward, values, cost, J's. I don't know what J stands for, actually. Anyway, So V star X is equal to maximum over U of the immediate reward plus the expectation of the reward to go. So in infinite horizon problem, one can prove that the optimal value function, so the value of the problem, assuming that you start at X and you follow an optimal policy, satisfies a fixed point equation, whereby V star X is equal to max over U of R plus expected cost to go, discounted by gamma, one step discounting factor. So we take this as a fact. There is a bit of a proof that uses some limit considerations. But again, from intuition standpoint, I'm trying to give you some justification. The justification is that this looks very similar to the Bellman equation, but in an infinite horizon setting, the recursive equation becomes just an equation. Yeah.
When you're solving these, how do you inform the algorithm to not keep searching? Because obviously, like with the discount factor, you can probably see at a point like clearly some earlier stopping point would be more optimal than the later one. But how do you distinguish like when it's not even worth to keep searching? Because maybe there is like some minimum like steps or whatever.
Yeah. So keep in mind that here, I'm not giving you an actionable algorithm yet. I'm just highlighting a key property of infinite horizon MDPs, whereby the optimal value functions satisfy an equation. How we translate this information into a search algorithm, that's something we'll see at the beginning of the next lecture. And basically, we can do it in a couple of ways: value iteration algorithms and policy iteration algorithms. For now, this is just a derived property of our problem formulation. Just so happens that if you're not interested in the optimal value function, but you're actually interested in the following question: if I give you any policy pi, what is the cumulative reward that that policy is going to collect? Turns out that the value for that policy satisfies a very similar fixed point equation. But now we don't have a maximization of a U anymore because we're fixing the policy. And then the computation of the U's are simply with respect to the policy pi that is given. Note that this is given to you, this is given to you. So assuming that X has a finite number of realizations, this is actually a linear system of equations with respect to the value function B. So you could potentially solve this equation by solving a linear system of equations.
Can you repeat why previously for dynamic programming, the cost function depended on the disturbance, but here?
Yes, here it depends still on the disturbance, but the stochastic dependency is more cryptically captured by this transition function. That is, T is the probability of going into a new state X prime given X and U. So it's what I was saying before. And here I made a little bit of a change of notation, as I mentioned, from the control theory notation to the computer science notation. So you can write sk plus 1 equal f of xk uk wk, and then say that wk follows some probability pk of conditional xk uk, or equivalently, you can say that, so what I give you is a p and f in order to compute the next x, or I can just give you this object t of xk plus 1 given xk uk. So this is directly the probability distribution of the next states given x and u. The two are actually identical. They can be mapped to each other. The difference then notationally, the dependence on disturbance here is explicit. Here is a bit more cryptic. But the point being, the dynamics are still stochastic, and the stochasticity is captured by the probability distribution over the next states given x and u. Note that this model is clearly Markovian in the sense that the dependence in the past is only with respect to the current value of the state x and the current action u. One more thing, and then we wrap it up. I'll talk about algorithms to solve for the infinite horizon Bellman equation next time. It won't be too long. It will need only 15, 20 minutes. There is an alternative way of writing the infinite horizon Bellman equation that seems very benign, but actually has been quite revolutionary, especially to derive learning-based algorithms. Specifically, let's define something that is referred to as a Q function. The Q function is simply the right-hand side of the infinite horizon Bellman equation. And it has the following interpretation. It is the cumulative word that you collect, assuming that you start at X, you play control U, and then you act optimally after them, according to the policy pi star. So if you are at state X and you use control U, and then you act optimally with, from the next stage onward, your cumulative cost is RxU plus the optimal reward to go from the perspective of the next state. But of course, the next state is stochastic, so you have to average the different realizations of the next state. So you say, who cares? I'll tell you in 1 second why you care. But first, I want to show that assuming that you care about the Q functions, the Q functions satisfy a fundamental equation that is essentially the same as the Bellman equation, but for Q functions specifically. And this seems to be like a little bit circuitous. So we said that the Q star is by definition Rxu plus gamma sum over next state X prime of the realization of the next states times V star X prime. So that's the definition of Q. But then we also have the condition that V star X, again, following our definition, is equal to max over U of Q star XU. So you plug this into here, and now you have a fixed point equation for the Q functions. Okay, so that's fine. But then the question for me should be, what do we care about the Q functions? In principle, you don't care about them. But let's assume, and of course we will revisit this setting at a great extent. Let's assume that now some part of the model are not known. So you don't know this probability distribution T. And you have some algorithm, learning algorithm, reinforcement learning algorithm, or imitation learning, I say reinforcement learning algorithm that allows you to learn approximately the Q functions. We'll see which algorithms we can use. So some part of the MDP problems are not known anymore, like the transition kernel is not known. But we're learning an approximation for Q. And now I'm asking you to compute the optimal action, given that you are at state X. So what do? Well, if an oracle gives you the Q star XU, then your optimal action is simply the one that maximizes the Q. Okay, so basically, if an oracle gives you the optimal Q function, then computing an optimal action is trivial. You just solve the optimization. Well, trivial. I mean, it could be a high-dimensional problem, but at least you have a way to do so. Say that actually the oracle gives you the V star function, the optimal value function. How do you compute the optimal action? Well, now the optimal action is going to be max of U of Rxu plus gamma sum of T X prime X U V star X prime. And so even if I give you the optimal value function, to compute the optimal action, you need to know the transition kernel. But if you're in a learning setting where we assume that we don't have access to the transition kernel, that becomes a problem. That's why this somewhat very benign reformulation of the problem has been extremely influential in order to derive learning algorithms, because that allows you to much more directly find actionable algorithm for optimal action estimation. Just to want to, the first time I saw Q function said, okay, this is completely useless. I mean, just writing one thing in terms of another quantity, why so? People typically don't really discuss that. But that's a big difference, that if you then reframe the problem through the notion of Q function, then tracking and optimal control action becomes much more natural in the setting where some elements of the MDP problem are is not known. For example, the transition probabilities. Make sense? So what we're going to see next time is a couple of algorithms to, given a policy, there is also an analog equation to compute a Q function for the specific policy. So Q pi xu is the value of the problem, assuming that you are at state x. You use control u, and then you use the policy pi for all stages afterwards. So what we're going to see next time is a couple of algorithms to solve the infinite horizon MDP problem, value iteration algorithm, and policy iteration algorithms. And then we're going to move into the topic of continuous time closed loop optimal control. We'll get back to infinite horizon MDPs and their extension to the setting on learning-based control in a couple of weeks.